Welcome to DAR Tutors. Today, we're covering some key concepts in graph theory from the IB Applications and Interpretation Higher Level curriculum. First, let's explore Euler paths and circuits. Our objective is to determine when we can trace a graph's edges in a continuous trail. We'll be looking at Eulerian and semi-Eulerian graphs. Before we define these, we need to understand the concept of a vertex's degree. The degree of a vertex is simply the number of edges that connect to it. In this graph, vertex A has a degree of 2 because 2 edges connect to it. Vertex B has a degree of 3. We call vertices with an even degree even vertices, and those with an odd degree odd vertices. Now let's define Eulerian and semi-Eulerian graphs based on these vertex degrees. A graph is Eulerian if it contains a closed trail that visits every edge exactly once. This is called an Eulerian circuit. It starts and ends at the same vertex. The condition for a graph to be Eulerian is very simple. Every single vertex in the graph must have an even degree. If this holds, you can always find an Eulerian circuit. If a graph doesn't meet this condition, it might still have an Eulerian trail. A graph is semi-Eulerian if it has a trail that visits every edge exactly once, but it doesn't return to the starting vertex. For this to happen, the graph must have exactly 2 vertices with an odd degree. The trail will then have to start at one of these odd vertices and end at the other. Any other scenario, a graph with 0 odd vertices is Eulerian, with 2 odd vertices is semi-Eulerian, means the graph is neither Eulerian nor semi-Eulerian. Let's apply these rules to a problem. We need to determine if a complete bipartite graph, denoted K subscript Mn, is Eulerian, semi-Eulerian, or neither. The graph K subscript 4.03 has 2 sets of vertices, one with 4 vertices and one with 3. Each vertex in the first set is connected to every vertex in the second set. Let's list the degrees of each vertex in our K43 graph. The vertices A, B, C, D in the first set each have 3 edges connecting to them, so their degree is 3. The vertices P, Q, R in the second set each have 4 edges connecting to them, so their degree is 4. We have found 4 odd vertices, A, B, C, D. A graph with 4 odd vertices is neither Eulerian nor semi-Eulerian. It has more than 2 odd vertices, so no continuous trail can visit every edge exactly once. So our conclusion for K4.3 is that it's neither. Now for a more general case, when is the graph K subscript Mn Eulerian? Remember, a graph is Eulerian if all vertices have an even degree. In K subscript Mn, the m vertices have degree n and the n vertices have degree m. Therefore, for all degrees to be even, both m and n must be even numbers. If m is even, all n vertices have an even degree m. If n is even, all m vertices have an even degree n. Finally, for which values is it semi-Eulerian? This occurs when there are exactly 2 odd vertices. This condition is met when m is 2 and n is any odd number, or vice versa. This would result in 2 vertices having degree 2 and n1 vertices having odd degrees. Let's move on to the Chinese postman problem, which is a practical application of Eulerian circuits. Our goal here is to find the shortest possible route that a postman can take to deliver mail along every street. The problem asks for a minimum weight circuit that travels along every edge in a weighted graph at least once and returns to the starting point. Essentially, we want to deliver mail on every street without wasting any time. First, if the graph is already Eulerian, meaning all vertices have an even degree, the problem is simple. The shortest route is any Eulerian circuit, and its weight is just the sum of the weights of all the edges in the graph. But what if the graph is not Eulerian? If the graph has odd vertices, we can't visit every edge exactly once and return to the start. The solution is to turn it into an Eulerian graph by duplicating some edges. Our task is to choose the edges to duplicate in a way that minimizes the total weight added to the route. Let's work through an example with a semi-Eulerian graph. Our objective is to find the minimum weight circuit for a postman. Here we have a graph representing a set of roads. First, we identify the degree of each vertex. A and D are odd vertices, and B, C, and E are even vertices. Since there are exactly 2 odd vertices, the graph is semi-Eulerian. To make the graph Eulerian, we need to make the degrees of A and D even. The most efficient way to do this is to add a path between them. In this simple case, the direct edge AD already exists with a weight of 2. By traversing the edge AD twice, we increase the degrees of both A and D by 2, making them even. This adds 2 to our total path weight. Now, let's calculate the total weight of the inspection. The original total weight is the sum of all edge weights. If we add the duplicated edge, the new total weight is 11 plus 2, which equals 13. The postman's route will have a total length of 13. A possible route would be A to B to C to D. Then, because we need to duplicate AD, we can go to A, then to E, back to D, and finally back to A. So, we've successfully made the graph Eulerian by finding the shortest path between the two odd vertices and duplicating it. What if a graph has more than 2 odd vertices? Let's tackle that more complex scenario. In this graph, let's identify the degrees. Vertices A, B, C, and D all have a degree of 3, making them odd. Vertex E has a degree of 4, so it's even. To make all these vertices even, we need to pair them up. There are 4 odd vertices, which means there are 3 different ways to form 2 pairs. We can pair A with B and C with D, or A with C and B with D, or A with D and B with C. Our objective is to find the pairings for which the sum of the shortest paths between them is the minimum. First, let's find the shortest path between every pair of odd vertices. The shortest path from A to B is the direct edge AB, with weight 8. From C to D, the shortest path is C to E to D, with a total weight of 5. For our second pairing, A to C via E has weight 7, and B to D via E has weight 7. Finally, the shortest path from A to D via E has weight 6, and from B to C via E has weight 8. Now we compare the total weights for each pairing. The first pairing has a total of 13, the second has 15, the third has 14. The minimum total weight is 13, corresponding to duplicating the paths A, B, and C to E to D. The original graph had a weight of 44. By adding our duplicate paths, the total travel distance is 44 plus 13, which is 57. A possible route would be A to E, then E to B, then B to A, duplicating AB, then to D, then D to C, then C to E to D, duplicating CED, then back to A. This process ensures we find the absolute shortest distance for the postman to travel. Now let's shift our focus to Hamiltonian graphs. In the last section, we were interested in visiting every edge. Now we are interested in visiting every vertex. A Hamiltonian cycle is a route that starts and ends at the same vertex and visits every other vertex exactly once. This is different from an Eulerian cycle, which visits every edge exactly once. So we are looking for a cycle that touches each vertex in the graph, one time only. Here's an example. We can trace the path A to B to C to D to E to F and back to A. Notice that each vertex is visited once, and we end up where we started. This is a Hamiltonian cycle. Sometimes, a graph has a Hamiltonian path but not a cycle. A path visits every vertex once, but starts and ends at different vertices. The route B to D to F to A to G to E to C is a path, not a cycle, because it doesn't return to B. Finally, we can classify graphs as Hamiltonian, semi-Hamiltonian, or neither. A graph is Hamiltonian if it contains a cycle. It's semi-Hamiltonian if it has a path but not a cycle. If it has neither, it's just a regular graph. Finding Hamiltonian cycles is much more difficult than finding Eulerian circuits. Unlike Eulerian circuits, there isn't a simple theorem based on vertex degrees. Currently, for any graph, we don't have a quick way to test if it's Hamiltonian. The standard method is simply trial and error, or inspection. Let's work through an example. We have this graph and we need to find a Hamiltonian cycle that starts and ends at A. Let's try to build a path step by step. From A, we can go to B to D or G. We can try the path A to B to C to D to E. From E, we can only go to F or G without repeating a vertex. If we go to F, we are stuck. So we need a different approach. Look at the vertices with a low degree. Vertex C only has edges to B and F. This means any Hamiltonian cycle must use both of those edges. For the cycle to include C, we must include the edge BC and the edge CF. This is a critical insight. Similarly, vertex E only connects to D, F, and G. For the cycle to include E, we must include 2 of its edges. Knowing this, let's try a new path. Start at A, go to G, then to D, then to C. Now we must go to F. From F, we can go to E or G. Since G is already visited, we go to E, and from E, we go to B. From B, we must return to A, which we can do. This works. We have our cycle. We have found a Hamiltonian cycle. By inspecting the graph and carefully choosing which edges to include, especially for vertices of degree 2, we can simplify the search process. Now we arrive at one of the most famous problems in graph theory, the traveling salesman problem. The problem asks for the shortest possible route that starts and ends in the same city and visits every other city exactly once. The key phrase here is exactly once. The salesman is not interested in revisiting cities. This is essentially a weighted Hamiltonian cycle problem. We are looking for the Hamiltonian cycle with the lowest total weight. Solving this problem perfectly is incredibly difficult for large graphs. For a graph within cities, there are n1 factorial over 2 possible cycles. For even 20 cities, this is an astronomical number of paths. The strategy we use is to find bounds. We want to find an upper bound, a guaranteed Hamiltonian cycle, which gives an estimate for the cost. And we'll find a lower bound, which is a value the true cost must be higher than. By finding a tight interval between the bounds, we can be confident in our solution. The first method we'll learn for the traveling salesman problem is the nearest neighbor algorithm. This algorithm provides an upper bound for the TSP. The algorithm finds a Hamiltonian cycle quickly. It's a greedy algorithm, meaning it makes the locally optimal choice at each step. Let's follow the steps for this algorithm. The algorithm is straightforward. First, you choose a starting city. Then, from your current city, you travel to the nearest city you haven't visited yet. You repeat this process until all cities have been visited. Finally, you return to the starting city. The total weight of this path gives you an upper bound for the TSP. Let's apply it to this graph, starting at A. From A, the nearest vertex is C, with a weight of 5, so we travel A to C. Now at C, the nearest unvisited vertex is E, with a weight of 7, so we travel C to E. From E, the nearest unvisited vertex is D, with a weight of 4. We travel E to D. At D, only B is unvisited. We travel D to B with a weight of 6. Finally, all vertices are visited. We return to our starting point, A, using the edge BA, which has a weight of 10. The cycle is complete. The total weight of our nearest neighbor cycle is 32. This gives us an upper bound. We know that the true minimum weight for this TSP must be less than or equal to 32. It's important to note that the result can depend on the starting vertex. The nearest neighbor algorithm is an heuristic. It provides a good solution, but not necessarily the optimal one. Now let's find the other side of our interval, the lower bound. For this, we use the deleted vertex algorithm, which involves finding a minimum spanning tree. The logic behind this is that any Hamiltonian cycle in a complete graph must pass through each vertex exactly twice. So, if we remove one vertex and its edges, the remaining path is a tree that spans the other vertices. The weight of this minimum spanning tree is the foundation of our lower bound. Here are the steps. First, we select any vertex and delete it from the graph, along with all edges connected to it. Second, we find the minimum spanning tree, or MST, for the smaller graph that remains. Third, we add back the weights of the 2 shortest edges that connected to the deleted vertex. The result is our lower bound. Let's use the same graph and calculate a lower bound by deleting vertex A. Step 1. Delete A and all its edges. We are left with a graph containing only vertices B, C, D, and E. Step 2. Find the MST of this remaining graph. We can use Kruskal's algorithm. We add edges DE 4, BD 6, and CB 8. This connects all vertices with a total weight of 18. Step 3. Now we look at the edges we deleted from vertex A. Their weights were AC 5, AE 7, AD 8, and AB 10. The 2 shortest are 5 and 7. Our final lower bound is the sum of the MST weight and these 2 shortest deleted edge weights, 18 plus 5 plus 7, which equals 30. This means the actual TSP cost must be at least 30. Combining our upper bound of 32 from the nearest neighbor algorithm and our lower bound of 30, we have narrowed down the answer. The minimum weight for this TSP is either 30, 31, or 32. In fact, by inspection, the optimal cycle is AEDBCA, with a weight of 7 plus 4 plus 6 plus 8 plus 5, which equals 30. Notice it matches our lower bound, confirming it is the minimum. We have successfully found the exact solution. So far, we've dealt with what's called the classical TSP, which assumes a complete graph and that the direct path between any two cities is the shortest. But this isn't always true in the real world. The practical TSP accounts for missing roads, one-way roads, or situations where an indirect route is faster or shorter than a direct one. Here, visiting a vertex multiple times is allowed if it leads to a shorter total distance. The solution involves a two-step process. First, we transform our practical graph into a classical one. Second, we solve the classical problem using the methods we just learned, like the nearest neighbor and deleted vertex algorithms. Let's consider this example. The direct path from C to D has a weight of 60. But if we go via E, the path is C to E to D, with a total weight of 25 plus 30, which is 55. Clearly, the indirect route is faster. To convert the graph, we create a new, complete graph. For every pair of cities that didn't have a direct road, we add 1 and assign it the weight of the shortest path between them from the original graph. For existing roads, like the one between A and B, we keep the original weight if it's the shortest path. If an indirect route is shorter, we replace the original edge weight with the shorter one. Once we have this new, complete graph with the shortest path weights, we can apply our standard nearest neighbor and deleted vertex algorithms to find an upper and lower bound, and hopefully the optimal solution for the practical TSP. We've covered Eulerian circuits, Hamiltonian cycles, and 2 major applications: the Chinese postman problem and the traveling salesman problem. These are powerful tools for optimization, but as we saw, the TSP can be very complex. At DAR Tutors, we specialize in expert tuition for IB, A-Level, and IGCSE. Whether you're struggling with a concept or aiming for a top grade, our personalized online and home tuition can provide the clarity and support you need. Contact us today to learn more. Now let's test your understanding with some IB-style practice questions. Work through them on your own, then come back for the fully worked solutions. Question 1 asks you to find the value of x that makes a graph Eulerian. Remember the key property of Eulerian graphs. Question 2 is a classic Chinese postman problem. Calculate the total degrees, find the odd vertices, and determine the shortest path between them. Question 3 is a TSP. First, transform the graph. Second, apply the nearest neighbor and deleted vertex algorithms to find the bounds. Question 4 asks for both Eulerian and Hamiltonian characteristics. Make sure you know the difference. And finally, question 5 is another practical TSP. Again, you'll need to find shortest paths and apply the algorithms. Welcome back. Let's go through the solutions together. Solution for question 1. For the graph to be Eulerian, all vertices must have an even degree. This means 4, 2, and x must all be even. Therefore, x must be an even number. Solution for question 2. Odd vertices. B and F. The shortest path between B and F is B to C to F. The weight is 2 plus 5 equals 7. The original sum of weights is 24. So the minimum distance is 24 plus 7, which equals 31 kilometers. A route is A to B to C to G to F to C to B to A. Solution for question 3. For the upper bound, starting at C and using the nearest neighbor algorithm, we get the cycle C, E, B, A, F, D, C with a weight of 2 plus 3 plus 6 plus 5 plus 7 plus 4 equals 27. For the lower bound, deleting C, the minimum spanning tree of the remaining graph has a weight of 18. The 2 shortest deleted edges are C to D with 4 and C to E with 2. The lower bound is 18 plus 4 plus 2 equals 24. The true solution lies between 24 and 27. Solution for question 4. For Part A, both Hamiltonian and Eulerian, a cycle graph C as indituant for n at least 3. For Part B, Eulerian but not Hamiltonian. All vertices are even, but there is no Hamiltonian cycle. For Part C, Hamiltonian but not Eulerian. A Hamiltonian cycle exists, but some vertices have odd degree. For Part D, semi-Hamiltonian and semi-Eulerian. A Hamiltonian path exists, and exactly 2 odd vertices. Solution for question 5. The graph is not complete. We need the shortest paths between all cities. For the salesman at B, the cheapest route. B to A, 25, to E, 30, to D, 45, to C, 35, to B, 105. The total cost is 240. Towns visited more than once are part of shortest paths used to connect the graph, for example, C, D, and E. Well done for working through these problems. Remember to revisit any concepts that you found challenging. For more help and tailored learning, don't hesitate to reach out to DAR tutors.